Greetings to one and all gathered here. I request everyone to be comfortable in your seats. A warm welcome to the opening ceremony of the International Conference on Mathematics for Data Science and Dynamics 2024. We stand here today at the crossroad of knowledge and innovation as Rajagiri Engineering College and Kerala Mathematics Association proudly presents ICMDD-2024. This conference promises to be a platform where brilliant minds from around the globe converges to discuss, collaborate, and chart the future of this dynamic field. Note that we have live streaming of the conference. Please check the conference website. I respectfully welcome Dr. Ram Kumar sir, the conference convener, to take a moment to provide a briefing of the conference.
Good morning, all. Welcome to the International Conference on Mathematics for Data Science and Dynamics 2024, an annual conference of Kerala Mathematical Association. This event is organized by the Department of Mathematics and Center for Topology and Applications, Rajagiri School of Engineering and Technology, and funded by Science and Engineering Research Board and National Board for Higher Mathematics. The conference aims to present and discuss the most recent innovations, trends, results, and concerns, as well as real-life challenges and possible solutions in the field of topological data analysis, data science, topological dynamics, graph theory, operator theory, stochastic process, and other areas. Data science combines math and statistics, specialized programming, advanced analytics, artificial intelligence, and machine learning with specific subject matter expertise to uncover actionable insights hidden in data. These insights can be used to guide decision making and strategic planning. Learning the theoretical background for data science or machine learning can be a daunting experience as it involves multiple fields of mathematics like topology, linear algebra, calculus, statistics, fuzzy logic, and set theory, number theory, probability theory, etc. Dynamical systems combines theoretical and numerical approaches to understand the dynamic behavior of models in mathematics and across most areas of science and engineering. Since the explosion of interest in chaos some 50 years ago, the idea that simple deterministic rules can generate complicated and unpredictable temporal behavior has been used to improve our understanding of physical and biological processes. For example, weather forecasts now routinely rely on aggregating the results of many forecasts based on slightly different initial conditions so that it is possible to assess the variability of predictions. These insights lead to two important directions of research. First, there are theoretical questions about the general properties of solutions of different equations and differential equations, including how the nature of solutions changes as external parameters are changed, and how additional structure in the equations changes the behavior of the systems. Secondly, there are issues around the creation of appropriate models for particular applications and analysis and interpretations of these models. The study of dynamical systems is the focus of dynamical systems theory, which has applications in a wide variety of fields such as physics, biology, chemistry, engineering, economics, etc. Dynamical systems are a fundamental part of chaos theory, logistic map dynamics, bifurcation theory, etc. The three-day international conference will focus on the current developments in these areas. It is also a forum for researchers to present their papers and discuss it with experts. The conference includes 7 plenary talks, 15 invited talks, and 28 contributory paper presentations. More than 100 participants have registered for the conference. Rajagiri School of Engineering and Technology and KMA will honor Professor R. Vikal Rao, Professor V. Kannan, Professor K.T. Joshi, and Professor A. Krishnamurthy for the inspiration and motivation extended to generations of students and also for their research contributions during the conference. The annual general body meeting of Kerala Mathematical Association will be held on 3rd February 2024. On this day, at 11 a.m., KMA will be honoring mathematics college university teachers from Kerala who retired during the period from March 2019 to June 2023. KMA is instituting Sri Vaikam Parameswarya Memorial Award for an eminent professor and mathematician who has proved his or her mettle in the field of Indian traditional mathematics as well as in modern mathematics. Dr. P. Rajagiri, son of Sri Parameswarya, has come forward to sponsor the award. The first Sri Vaikam Parameswarya Award will be given during the general body meeting of KMA. Let me call Benjamin Franklin. God begins. Tell me, I forget. Teach me, and I remember. Involve me, and I learn. God ends. Let us involve ourselves and open new areas of knowledge which will enhance the learning process. Thank you.
Thank you, sir, for the briefing. So let's start our official opening session of this conference. Let me take this opportunity to welcome our dignitaries onto the stage. May I invite Professor Shivaramakrishnan R., Vice President, Kerala Mathematics Association, Reverend Father Dr. Jose Kuriel CMI, Director, Rajagiri Engineering School, Technology, Dr. P.S. Vijay, Principal, Rajagiri Engineering School and Technology, Dr. K. Paulus Jacob, Dean of Research, Rajagiri School of Engineering and Technology, Father Dr. Jason Paul Mulirikal CMI, Vice Principal, Rajagiri School of Engineering and Technology, and Dr. Paul Isaac, General Secretary, Kerala Mathematics Association, onto the dais. To begin this auspicious occasion, let us first invoke the blessing of the Lord Almighty. May I request all of you to please rise for the invocation.
അച്ഛനും അമ്മയും എന്തു പറഞ്ഞാലും അക്ഷരം തെറ്റാകലും സരിച്ചും ഉള്ളിൽ വെളിച്ചം പകരും ഗുരുവിനെ ഉന്നയിൽ സ്നേഹിച്ചു ആദരിച്ചു ഈശ്വര കൈകൂപ്പി നിൽപ്പു ഞാൻ മുന്നേ ഈരനണിഞ്ഞ മിഴികളോടെ കാരുണ്യമെന്നിൽ ചൊരിയണേ ഭൂമിയിൽ കാരണമായുള്ള തമ്പുരാനേ കാരണമായുള്ള തമ്പുരാനേ.
I am delighted to invite a distinguished academician, visionary leader, Dean of PG Studies, Exam Controller of Rajagiri Engineering College, Dr. Vinod Kumar, to welcome the gathering.
Welcome to the International Conference on
Mathematics for Data Science and Dynamics, together with the annual conference of Kerala Mathematical Association. The 3 days conference is meant for sharing the recent advancements in the areas of topology, linear algebra, graph theory, quantum information theory, stochastic process, which are applied to data analysis and study of dynamical systems. For the opening session today, on the dais we have with us Professor R. Sriramakrishnan, retired from University of Calicut, Vice President of Kerala Mathematics Association, to present our meeting. May I warmly welcome Professor R. Sriramakrishnan to this meeting. Reverend Father Dr. Jose Kulian, CMI, the Director of Rajagiri School of Engineering and Technology, is always behind us, supporting and guiding all our engineers. I warmly welcome our Director, Reverend Father Dr. Jose Kulian, CMI, to this meeting. Dr. P.S. Riddle, retired from Cochin University of Science and Technology, is an inspiration to all academic activities of this institution. I warmly welcome our Principal, Dr. P.S. Riddle, to this meeting. Our Father Dr. Jason Paul Bullock, CMI, our Vice Principal, is involved in all the activities of this institution. I warmly welcome our Father Dr. Jason Paul, CMI, to this meeting. Dr. Paulo Jacob, our Dean Research, retired from Cochin University of Science and Technology, as Vice Chancellor, gives support to all our research activities. I warmly welcome Dr. Paulo Jacob to this meeting. Dr. Paul Tyson, General Secretary of Kerala Mathematics Association, has been working with us for the last 1 month to organize this conference. I warmly welcome Dr. Paul Tyson to this meeting. I welcome all the resource persons, especially Professor V. Kannan, who took a lot of pain and effort to come from Vijayawada to this meeting. Welcome, sir. I welcome all the delegates to this meeting. I welcome our Assistant Director and Dean UG, Reverend Father Dr. Joel George, all other Reverend Fathers to this meeting. Let me welcome all my colleagues and students to this function. Thank you all.
Thank you, sir, for addressing the audience. It's my distinct honor to welcome a distinguished scholar, a prominent figure in the field of mathematics, and the Vice President of Kerala Mathematics Association, Professor Sriramakrishnan, to address the audience.
Respected Father Jose Kulian, Director of RSET, Reverend Father Benny Nalkara, Sri V.S. Srijit, Principal, and Dr. Vinu, Coordinator of this conference. I am indeed very happy to be here in the midst of youngsters for the privilege that has been granted to me by the organizers of this conference. I am particularly grateful to Dr. Vinod Kumar, who has been constantly contacting me about my welfare and about my coming to this institution. In fact, there are all little problems, but these are the moments which I cherish. I am very happy that I am with you all. The first thing that I have to do is to thank the organizers, especially Father Jose Kulian, Reverend Benny Nalkara, Srijit, and Vinu for the opportunity given to me to be present on this occasion and to speak a few words. I am not very familiar with the area of data sciences. So what I did was, I contacted my younger granddaughter who is doing a course in, I think it is biology and related topics. She gave me a note on what are the aspects of data science. Let me just give a brief account of what I know or what I have gathered from my granddaughter. Her name is Krishna Vaidyanathan. She is doing graduate studies at the University of Texas at Austin, USA. It so happened that both the granddaughters are in USA. Data science is a field of computational modeling and analysis that utilizes algorithms, formulae, and models. Data scientists speak of big data, machine learning, and natural language processing around the mean distribution or mean or data distribution or the shape with which the data is spread over the mean. The concepts of mean, standard deviation, residual, sum of squares, and normal distribution have relevance to analysis of data. Analysis of data have greatly improved with the help of probability and statistics. It is reported that William Playfair of Scotland provided the early framework for data visualization and data explanation during the period AD 1780 to 1820. Recent developments indicate the emergence of a branch of science called data science, which is meant to collect data sets, do analysis for improved decision making, and make predictions. It was Blaise Pascal, AD 1623 to 1662, a noted French philosopher who made brilliant experiments in hydrostatics and pneumatics and properties of air, that is, about the properties of air and other elastic fluids and gases. Next came Laplace. Then he was a French mathematician and an astronomer whose researches on motion of planets and theory of probability earned him the title of Newton of France. From 1774 onwards, he wrote many memoirs on the subject, the results of which he embodied in the classic Theory Analytic des Probabilities of 1812. Laplace also wrote that at the bottom, theory of probability is only common sense expressed in numbers. It was only in late 1990s that the term data science became popular. It originated from a need for statisticians to collaborate with data scientists to bring mathematical models to suit process of analysis of data sets. One major goal of data science is to extract patterns. These patterns are then studied and analyzed to help improve decision making and make predictions. For instance, in health science, a physician may collect large number of patient data and on analysis, he or she hopes to analyze the potential risk factors on abnormal situations. To sum up, the science of data sciences holds vast potential for mathematical modeling. The vast number of well-developed machine learning algorithms speaks well about the growing need for data science in other areas as well. It has the potential for improving the living standards of mankind. It is important that we establish ethical practices and critical analysis while understanding and explaining the benefits of data and sciences to the public. I am thankful to you all. With these few words, I conclude. Thank you all for the kind invitation extended to me for going over here and to do the formal inauguration of the conference of the 3-day international conference on data sciences. I hereby declare that the conference is open.
Your presence and word of encouragement will greatly enhance the significance of this event. Thank you, sir. The lighting of the lamp is a universal symbol, representing dispelling of darkness and arriving of the light. It is the start of something new, like turning on the light to guide us on a journey of knowledge and success. I extend a warm welcome to all dignitaries to join us in the lamp lighting ceremony, marking the inauguration of the function. Thank you all. It's a privilege to invite a true visionary and a source of inspiration, our director, Reverend Dr. Jose Create CMI for the inaugural address.
Professor R. Shivaramakrishnan, Vice President of Kerala Mathematical Association and the President of this opening session of International Conference on Mathematics for Data Science and Dynamics. Dear Professor Dr. P.S. Sridhar, the Principal of RSET, Reverend Dr. Jason Paul, the Vice Principal, Professor Rajagiri, Dean Research at RSET, Dr. Paul Isaac, General Secretary of KMA, Professor Vinod Kumar, Dean PG Studies, Dr. Vinod, Head of Department of Mathematics, other resource persons and participants of this conference, my personal cordial welcome to all of you and hearty greetings. I congratulate the faculty in the Department of Mathematics and the Center for Topology and Applications for organizing this international conference on mathematics for data science and dynamics for serious academic interactions in this field and on this discipline. Mathematics, as we all know, is the foundation or base of all sciences. So the developments or growth in any aspect of this science affects or has impact on almost all other sciences. So such conferences make us repeatedly vigilant and alert to such changes as we bring together researchers and academicians in this field and provide a forum to present their findings and exchange their opinions and evaluations on their findings. I see an array of several great mathematicians and scientists standing ready to contribute their share to this vast treasury of mathematical knowledge. It's a great achievement on the part of the organizers to contact them and bring them together in a forum of serious exchange of mathematical knowledge. And we are also very privileged that RSET could host this program through the contacts of the mathematics department. I learned that 4 eminent mathematicians will be honored by KMA and our college for their unique contributions for the study of mathematics. R. Vithal Rao, V. Kannan, K.D. Joshi, and A. Krishnamurthy, all of whom have held very important positions and discharged very heavy responsibilities during their career. My humble greetings to all of them in advance. They will be formally honored, as we know, on the day after tomorrow. Now, for the sake of those who attend this conference online or offline and come into contact with the Rajagiri School of Engineering and Technology for the first time, a word about our institution and its culture of quality education and pursuit of excellence. It is one of the constituent units of a Rajagiri group of higher educational institutions and was established in 2001. It was started as part of an ongoing endeavor by the priests of the Congregation of Carmelites of Mary Immaculate, or as CMI fathers, as we are popularly known, to take creative steps in the field of education, following the legacy of our founder, Saint Kyriakos Irias Chavra, who believed that education and spread of knowledge is the only means for transforming the then static Kerala society of the 19th century into a dynamic one, and initiated an educational movement at that time throughout the breadth and length of Kerala and paved the way for a vast change in the society. And we know from the time of Enlightenment and Industrial Revolution in Europe, the Western society began to get transformed into a dynamic one. But nothing happened in our own society due to the widespread of illiteracy, ignorance, and the consequent rigid culture of traditionality, with its manifold superstitious practices and social evils, caste and its religious discriminations and divisions. It is with the objective of opening the inner eyes or creative intelligence of all human beings, or in other words, enlightening and empowering the society, the first CMI fathers and their education institutions were founded 2 centuries back. Today, there are more than 800 education institutions ranging from lower KG to professional colleges and to a university spread in different parts of our country and abroad. And we try to sustain and grow in us and in all those who are working with us the creativity of our founding fathers, and to give our humble leadership in helping the society to get transformed continuously as it moves on. The Rajagiri institutions among the CMI institutions stand out as reputed models of excellence and innovation. Regarding RSET itself, it is one of the premier institutions of engineering education in Kerala and is the first private engineering college in the state to be included in the NIRF ranking. It has A grade in NAC accreditation and its courses are NBA accredited also. In 2020, it was given autonomous status as one of the 3 autonomous engineering colleges in the state of Kerala. It has 9 BTech programs with 14 batches, 5 MTech programs, and has recognized PhD centers in 8 different disciplines. Having more than 3,700 students on the roads, it is also one of the largest engineering colleges in this part of the country. It provides excellent facilities not only for higher education and research, but also in placements, opening up to almost 90% of the students. It has a well-equipped infrastructure for student entrepreneurship, incubation, and startups, and wide network of tie-ups as well as dynamic interaction with industry. We have also student exchange and internship programs with the several universities in Germany, Japan, Australia, and United Kingdom. Apart from what it can do by itself, we do also by joining hands with other organizations and institutions in all feasible creative ways. This conference itself is a humble attempt in this direction by RSET, which functions in partnership with several reputed colleges and organizations and universities across the globe. With my best wishes and prayers for the success of the conference, I remain. Thank you very much.
Thank you, Father, for the kind words. I would like to call upon our Honorable Principal, Professor Dr. P.S. Srijit, to share with us his word of wisdom on this inaugural session.
Good morning, all. Respected President of the Function, Professor Sriramakrishnan, our Director, Reverend Father Dr. Joseph Uriyaratha, our Vice Principal, Reverend Father Dr. Jason Bond Malariya, Dean Research, Dr. Paulus Jacob, Dr. Paul Isaac, General Secretary of Kerala Mathematics Association, Reverend Father George Dr. Pulori, Dean UG Studies, Father Rajesh, Professor Kannan, Professor Vijay Kumar from Cochin University of Science and Technology, Dr. Vinod Kumar, Dean UG Studies and Control of Examination, Professor Ram Kumar, Dr. Vinu, Head of the Department of Mathematics, heads of other various departments of Rajagiri School of Engineering and Technology, Reverend Fathers, staff members of other institutions and our institution, and dear participants for this international conference on mathematics for data science and dynamics. At the outset, I take this opportunity to welcome all the participants of this international conference to our institution, that is Rajagiri School of Engineering and Technology. Secondly, I also congratulate the Department of Mathematics as well as the Center for Topological Studies of our school for conducting this international conference. I hope there are, as Dr. Ramkumar has already been explained, there are different sessions which will enlighten the participants on the mathematical applications of data science as well as dynamics. From an engineering point of view, if I talk about data science, in the era of big data, data science has emerged as a powerful force driving innovation across various industries. Defined as an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract insights and knowledge from structured and unstructured data, data science has become an integral part of decision-making process. Data science wields transformative power across industries in healthcare, finance, marketing, and manufacturing. It propels better decision, heightened efficiency, and innovative solutions. Analyzing vast data sets provides valuable insights, optimizing processes, and ensuring a competitive edge.
Data science impact is poised to deepen across diverse sectors. In healthcare, it will shape personalized medicine, optimize treatments, and predict disease outbreaks. Likewise, in finance, it refines risk assessments, fortifies fraud detection, and enhances customer experience. Crucially, data science empowers decision makers by offering real-time analysis for strategic choices and improved outcomes. As we advance integrating artificial intelligence and machine learning into data science will amplify predictive analytics and decision support systems. Regarding dynamics, or in general, it can be called as dynamical systems. It is the branch of mathematics devoted to the study of systems governed by a consistent set of laws over time, such as difference and differential equations. The emphasis of dynamical systems is the understanding of geometrical properties of trajectories and long-term behavior. Over the last 40 years, with the discovery of chaos and strange attractors, dynamical systems theory has gained considerable interest and has been found to have tentacular connections with many different areas of mathematics, such as number theory and topology. And science, dynamical systems can model an incredible range of behavior, such as the motion of planets in the solar systems, the way diseases spread in a population, the shape and growth of plants, the interaction of special pulses, or the processes that regulate electronic circuits and heartbeats. And I hope this conference will be throwing more light on such aspects of the data science as well as the dynamics related to the mathematics. And I take this opportunity to wish all success to this conference. Thank you very much.
Thank you, sir, for your inspiring words. Now I welcome the man of distinction, an idea of knowledge and experience, Father Dr. Jason Paul Numerical CMI, Vice Principal, Rajagiri Engineering College, to felicitate the gathering.
The respected President of the function, Professor Sivaramakrishnan, respected Director, Father Dr. Thomas Kuriyev, our Principal, Dr. P.S. Vijay, Dr. Paulus Dept, our Dean, Father Dr. Joel Jones, Associate Director, Father Ritish, our Education Counselor, Father Major, and respected members on and off the dais, the participants of this conference. First of all, I like the title of this conference. It is the International Conference on Mathematics 4. That 4 is important, data science and dynamics. So Maths 4 something. This is, I think, what we call it as applied mathematics. And when I looked into the program, I could see a very notable session. The title goes like this: The Marriage of Mathematics with Engineering. I like that marriage. And that also tells us a story. Maths is related to something, as we all know. The applied science is called technology. So the relevance of maths in an institution like ours and to general topic is that it is related to our day-to-day living. It is related to the things that we need to use in our day-to-day life. And very recently, I got a call from a publishing house. They asked me to write an article on the ethics of AI. Okay. Because we know that this is a hot topic, AI or ML and machine learning, etc. It is all related to what we discuss here, that is the data science. And in my opinion, the ethics of AI is a mathematical problem. Because in the AI ML algorithms, as we know, we got a black box. We put our data into a black box and finally we get the results. Because inside the algorithm, we've got so many layers and we do iterate on these layers that we call epochs. The problem is, the algorithm will give you finally a result, but maybe, we validate the result and we say that the accuracy is 90, 95%, etc. But the problem is how this algorithm came into this conclusion that is still unknown. How the AI works inside the box that is still unknown. It is basically mathematical formulas. And that's why we got a new branch of AI that is coming into the forefront at the moment, that is explainable AI. So what is happening inside that box? We need to know what is the rationale behind the results that we are getting out of this data, which is going through these layers and epochs and finally getting the outcome. Unless until we can understand what is happening inside that, we cannot have anything. Can you explain? Because we know that the classical problem in the ethics of AI is the huge data, the legal data, especially in the US, they are put into the supercomputers, which is processing the data through AI ML algorithms. And the studies have found out that the recommendations given by these systems, AI ML systems, to the maybe the lawyers and advocates, it is actually not favorable to the black people, the colored people. This is because of the problem with the data. Because previously, all the verdicts, because there was a bias inbuilt in the human mind, a kind of racism, and that was the verdicts. And because of that data problem, the AI algorithms researches solutions or give a recommendation in such a way that for a particular crime or an offense, the punishment that is given to a colored or a black people is much greater than that to a white or Caucasian person. So that is proven. And since the data is like that, and we do not know what is happening inside the AI box, we cannot act on it. So if we want to solve this problem, we should be able to understand what is happening inside that AI box, the algorithm box. And that is another very big problem. And I would say that the Kerala Mathematical Association and this conference itself will stimulate, will start some conversation regarding this, because I think this is going to be the next big thing that we need to have. And finally, come up with a solution. But once we understand how it is being rational, how it is being done, then we can maybe correct that. Maybe 2% or a little bit of factor. We say that bias is 2%, so we are changing that 2%. I don't know how to say that. And I call it as the God factor, because ethics comes from divine and God. So if we can introduce that God factor into this through some mathematical modeling, and that will be the solution to the ethical problems in AI and in our day-to-day life, in data, in general. So with this small little thought, I extend all the blessings and good wishes to this conference. I'm sure that there are so many people who work behind this, especially the mathematical department over here, Dr. Vinu, Dr. Vinod, Ramkumar, etc., and all others. And the KMA has also given a lot of effort into it, and wish you all the very best. Thank you so much.
Thank you, Father, for your inspiring words. Now I welcome the sculpture of human character, a seasoned scholar, a navigator of knowledge, Dr. K. Paulus Jacob, Professor and Dean of Research and Development, Rajagiri Engineering College, to facilitate the gathering.
President of this inaugural year, respected Professor C. Ramakrishnan, Vice President of the Kerala Mathematical Association, Director of our institution, esteemed Reverend Dr. Joseph Periodus, Principal Professor Sridhis, Vice Principal Reverend Dr. Jason Paul Mudayikil, Secretary of the Kerala Mathematical Association, Dr. Paul Isaac, Dr. Vinod Kumar, Professor Kanan, my earlier colleagues, Dr. Vijay Kumar, Dr. Nambudiri, Reverend Dr. Joel Kului, Reverend Father Rajesh, Reverend Father Major, heads of departments, colleagues, participants, ladies and gentlemen. Today is yet another day which is special in the annals of Rajagiri School of Engineering and Technology. Probably it is going to be memorable days for the participants as well. Going through the schedule of events, we can see the organizers have taken care to strike a balance between several plenary talks, invited talks, and also the contributed papers, giving excessive stress on the quality. I think the organizers need to be congratulated, especially the Center for Topology Applications, conducts such academic events regularly. I think it is this factor, regularity, which earns esteem for the conferences and other academic events conducted by this institution. I must also supplement what our esteemed director was mentioning. We try to follow the doctrine of no compromise on quality. All our processes, systems, as well as infrastructure adhere to that doctrine. So also this event. So the next 4 days are going to be intellectual nourishment to all the participants, those who are present here as well as those who are attending online. I remember this regularity is also a mathematical phenomenon, which has got its applicability in dynamics as well, so also in mechanics. What I remember as Hamiltonian mechanics or something like that. I only remember the terms, nothing more than that. We have several papers, several talks based on all these things on the topic of mathematics for data science and dynamics. Data science over the years have earned much prominence in the research field. One factor I would say which has facilitated this excessive amount of data being generated is the connectivity that is existed around the world. In one of the reports which I could read some time ago, it was mentioned that around 2/3 of the human race is connected to the internet. So also there are several devices like sensors. It is these sensors which have contributed to generating this what we call the big data. And if you want to make it useful, then you have to analyze. So data analysts, I think these days are essential for any industry, for any group, any business organization, so that they can do a self-analysis. Even institutions like us, we do a self-analysis, but the amount of data available is not that enormous. We did not have to apply any tools or any artificial intelligence tools or anything like that. As it has been mentioned here, most of these tools are based on algorithms, based on linear algebra, calculus, statistics, and things like that. So, in the present state of affairs, our government of India has proposed or even set up what is called an India Data Management Organization based on their policy of National Data Governance Framework. A lot of new terms have come up: data governance, data democratization, data fabric.
And these days, data as a service is also popular with the advancement in cloud computing and all that. So everything is available through the net. You can do the analysis based on various tools that are available, but all those things need to be made familiar to all the researchers. One constraint that researchers researchers face in this particular context is the non-availability of data sets. That is what is being tried to be filled up, the gap being filled up by the India Data Management Office. They are trying to build up, generate data, anonymize data, which are personal, and also collect all data from different sources and then form a database of data sets. And these data sets definitely will be of use to researchers. So that is where we stand now, as I have read recently one of the reports given by the government. So we need to be familiar with all these things. Then only we will be able to utilize the appropriate data set for our research and derive results which could be useful to all of us. There is also one school of thought that the curriculum in mathematics in higher education is not giving due importance to the mathematics to be applied to solve real world problems. Maybe events like this, debates like this, conferences like this, try to make more sensible usage of algorithms based on applications of mathematics in order to solve real world problems. I wish to congratulate all the participants. Let me wish all the best to all of you. The coming days are going to be wonderful. This institution will see that you are well taken care of. I thank the organizers. I acknowledge those who have contributed online as well as otherwise by giving lectures with the appropriate topics. Wish you all the best. Thank you.
Thank you, sir, for your kind words. I take the privilege to request Dr. Paul Isaac, General Secretary, Kerala Mathematics Association, to address the young delegates and motivate them by his words of wisdom.
Good morning to all. Respected Professor Sri Rameshwaran R, Vice President of Kerala Mathematics Association and President of this meeting. Reverend Dr. Jose Kuriyadat, Director of this institution. Dr. P.S. Sridhar, Principal. Dr. K. Paulus Peter, Dean of Research. Dr. Jason Paul Kodekil, Vice Principal. Professor V. Kannan, former PVC of Central University, Hyderabad. Dr. Devkumar Sir, Dr. Madhuri Sir, and other esteemed guests, distinguished scholars, respected delegates, and honorable members and reverend fathers. With great privilege, I stand here today as the General Secretary of Kerala Mathematics Association on the occasion of the annual conference and the International Conference on Mathematics for Data Science and Dynamics. On behalf of KMA, first of all, I would like to thank the management, the principal of Rajagiri College of Engineering for hosting the annual conference of Kerala Mathematics Association and for conducting this international conference. This conference stands as a testament to the collaborative spirit within the mathematical community, bringing together scholars, researchers, and enthusiasts from around the world. The knowledge shared and the discussions that will unfold during this conference are bound to contribute significantly to the broader mathematical discourse. Also, I would like to express our appreciation for the distinguished speakers and participants who have contributed to the success of this conference. Their commitment to the field of mathematics and their invaluable
insights are sure to enrich the experiences of all those present here. In this occasion, let us take a moment to recognize the exemplary leadership of Professor T. Krishnan, our beloved T. Sir, who is all in all of KMA. At present, the president of KMA. He is not present here because of his health problems. His guidance and vision have been instrumental in shaping the trajectory of the Kerala Mathematical Association. And we owe a debt of gratitude for his tireless dedication to the cause of mathematics. His legacy serves as an inspiration for all those involved in the pursuit of mathematical knowledge. I also acknowledge the invaluable contributions of the entire team here under the leadership of Dr. Vinod Kumar, Dr. Ram Kumar, Dr. Binu, and the entire mathematics department for their outstanding efforts in organizing this event. This department is, this is not the first time this department is hosting the annual conference of KMA. Yesterday I saw a list of conferences organized by this department under the leadership of Professor Vinod Kumar. I think this is the second or third time the department is hosting the annual conference of KMA. And I especially thank the Rajagiri institution and the department for hosting our conferences. The dedication and meticulous planning and hard work of this team have undoubtedly played a pivotal role in ensuring the success of this event. As the General Secretary of KMA, I wish all success to this program. With these words, I conclude. Thank you.
Thank you, sir. We, the Mathematics Department of Rajagiri Engineering College, is very delighted to release the magazine titled Sigma. Sigma represents the totality, which is significance of mathematics. Flipping over the pages, we will see that it contains several interesting articles, not only to the mathematical community, but also to the wider range of knowledge seekers. I now invite Dr. Professor Kannan to join us on the stage for this momentary function. I also extend a warm invitation to Reverend Father Dr. Joseph CMI to release the magazine and present it to Professor Dr. Kannan. I also request all the editorial members to join us on the stage. Unity is strength when there is a teamwork and a collaboration. Wonderful things can be achieved. Congratulations to Team Sigma and great thanks to everyone who contributed to the magazine. Now I invite Dr. Binu R., Head Department of Mathematics and Coordinator of the conference to express gratitude on behalf of Rajagiri and KMB.
The most respected dignitaries on the dais, respected resource persons and delegates, faculty, colleagues, and invited guests. A warm good morning to all of you. As we conclude the inaugural session of ICMDD-2024, it's my honor and privilege to extend a heartfelt gratitude to all who are present here and those who have worked hard
behind the scenes for the success of this program. First and foremost, I would like to express our deepest appreciation to our esteemed management and administration, Reverend Father Dr. Joseph Kurian CMI Director, Professor Dr. P.S. Richard, Principal, Father Joel George Pulloni, Dean UG Studies, Father Dr. Jason Paul Medical CMI Vice Principal, Dr. K. Paulo Stato, Dean Research, for providing us with their invaluable guidance and encouragement right from the initial phase of ICMDD 2024. We extend our sincere thanks to the President of the opening session, Professor Shivaramakrishnan Sir, Vice President KMA, and Dr. Paul Isaac, my Guru, General Secretary KMA, for their valuable presence here and providing us with their unparalleled and substantial support in organizing KMA's annual conference on our campus. We extend our heartfelt gratitude to our resource persons, distinguished guests, and delegates, and all others who have accepted our invitation and joined us today. Let me also place on record our gratitude to the brain and dynamics of this conference, our Vinod Kumar Sir, convener Ram Kumar Sir, all our colleagues and research scholars of the Mathematics Department. Your teamwork and tireless effort have made this conference a reality. I would also like to express our sincere thanks to organizing committee, heads of the various departments, teaching and non-teaching staffs, and technical team for this kind support. We also want to acknowledge our sponsors, National Board of Higher Mathematics and DST Sir. We are confident that the next couple of days will be filled with fruitful exchange of ideas and new connections in dynamics and data science. Once again, thank you all for being a part of International Conference on Mathematics for Data Science and Dynamics. Let me conclude by wishing all delegates a rewarding and enriching experience. Thank you very much.
Thank you, sir. As we come to the end of this opening session, on behalf of everyone here, we would once again like to thank our esteemed guests for gracing us with their esteemed presence today. Thank you everyone for joining us and showing your appreciation and gratitude. Have a wonderful day. So now let's break for a tea. So next session will resume by 11:40. Starts with the plenary talk by Dr. V. Kalla.
happened to be a student of young Venkataraman, whom I knew very much. He took his PhD from Madurai Kamaraj University in 1971. He worked at Madurai University, then Central University of Hyderabad, and at SERB University. He was the he is presently the Vice Chancellor and Vice Chancellor of Central University of Hyderabad. He was, I should say that. Published around 80 papers and produced about 15 PhDs, all to his credit. He is a fellow of Indian National Science Academy and a fellow of National Academy of Sciences. He has also won several awards. Personally speaking, I have more to say. He happens to be a student of late Professor M. Venkataraman of Madurai Kamaraj University. And Madurai Kamaraj University was doing equally well, just like Madras University. And they were producing a good number of researchers and teachers of mathematics. I have pleasure in inviting Professor Kannan to give his talk at this moment. Professor Kannan.
Thank you, sir. Thanks to Professor Shivaramakrishnan, sir, for his nice and affectionate words. I'm going to talk about some recent results in the dynamics of the real life. The time given to me is 1 hour. I will take nearly an hour. Our story starts from 100 years ago. I'm going to present 4 or 5 theorems now, which are new, but they are not very sophisticated. They can be understood even by the students. I start with a result of Banach, well known to the students as contraction mapping theory. For my first result, this is the starting point. Everyone knows the statement in one particular form, but I am going to state it in another version too. If X is a complete metric space, and if F from X to X is a contraction map, then F has a unique fixed point. Contraction map means to take any two elements in the domain X, take the distance between them, take their images, here images are also in the same space, take the distance between them. This F is contracting means this distance is smaller than this distance. We want it uniformly smaller in the sense that this is always less than or equal to some contraction constant C times dxy, where for some 0 less than C less than. If this happens, I said it is a contraction band. On any complete metric space, if you take any contraction band, there will be a unique fixed point. Now, I want to bring dynamics into this. Of course, it is already there in Banach's proof, even though that word is not come. If you take an element x in x, this map F is treated as a rule of mode. Within x, motion is happening. X is, we usually say that x goes to fx. We use the word goes to, but I actually mean it. When I say there is a dynamics, this point is moving to that position. Position is changing. After that, if I apply f once again, this fx goes to f of fx. I'm thinking that after 2 instants of time, this point is moving to this point. I'm bringing in time up. This again goes the third instant to f of x. And so on. I will use this notation by putting n in the superfix to say that this is f3 of x, this is f2 of x, and so on. Fn of x is Fn is the n-fold composite of f with itself n times taken. Then this itself, x is a moving particle, and these are the positions to which it moves. This I call as the trajectory of x, or more precisely, the sequence x and x is called the trajectory of x. I will even put n equal to 0 to infinity to say that I start with x. This is called x0 of x. Then rotate. Now, in the opening session itself, when somebody was explaining what dynamics is, he used the word long-term behavior of the moving objects. When objects move according to this rule of motion, that is according to this formula, movement is happening within x for all points. Then what will be the long-term behavior of that? Long-term behavior means if n is large, what will happen to f of x? This, even though these terms were not introduced, Banach himself proved that. F has a unique fixed point. Suppose that fixed point is x naught. He proved that for every x in x, this trajectory x and x, as n tends to infinity, converges to this x naught. In fact, in the proof of the contraction mechanism that we all learned in the textbook, this is already included in the proof. Therefore, we say that x naught attracts all x. Everything is coming nearer and nearer to x naught, and finally the trajectory is converging to x naught. One term that we use is this globally attracting. We say that this unique fixed point x naught is globally attracting. Its basin of attraction is the whole space. Wherever you start, it will move. Eventually, if long-term behavior is it will end up with x naught, it will go nearer and nearer to x naught. Therefore, in this theorem, in addition to the assertion that there is a unique fixed point, there is also an assertion that that fixed point is globally attracting, and therefore the long-term behavior of every point in the complete metric space is similar. Everything is going to that x naught. This is where we start now. the 4 or 5 results that I am going to mention today are about something called orbit type. If you take an element X, at present I am going to work in real number system as my X. That is the complete metric space. I am going to consider contractions on that. The simplest example is f of x equal to x by 2. That's a contraction on the real number. And I am looking at the orbit type of x, that is the sequence x, fx, fy and x. As I mentioned earlier, Fy stands for f of x, etc. And considering its order type, which term is less than which other term and so on. This is too simple. In this case, if you take, for example, x equal to 1, this sequence becomes 1, 1 by 2, 1 by 4, 1 by 8, etc. And this sequence is strictly decreasing, and it converges to a number 0, which is the unique fixed point here, and therefore the orbit type is very easily described as a strictly decreasing sequence. But it need not always happen like that. For a contraction map, there can be other types also. Because this notion is in the background of all the 4 or 5 theorems that I'm going to state, and first defining it leisurely. If you take 2 sequences of real numbers, I say that they are of same order type. If there is an increasing bijection from R to R, which takes this to this, such that for the bijection, if I give the name H, such that H of AN equal to BN for every n. If an increasing bijection takes this sequence to this sequence, then I say that they are of the same order type. It follows that AN will be less than AN if not only BM is less than B. Less than also I can write. The same order type means the nth term here, how is it varying with respect to the nth term? That is same answer for this. Now, order type means the equivalence classes are same order. Order type is the set of all elements having the same order type in a given particular element. Here in this example, I found that for this there is one order type. If instead of 1 I put some other element like 3 by 4, then next will be 3 by 8 and so on. And I am finding that this is the same order type, this is also strictly decreasing. But if I take the element minus 1, under the same contraction mark next to minus 1 by 4 and so on. This is of a different order type because it is increasing. If you take 0 itself, then 0, 0, 0, etc. That is the third order type because it is constant, not this other type. And then it is not difficult to prove these are all simple easy observations to say that for this there are exactly 3 order types. Namely the 3 order types that are meant to be here, and calling them as orbit types. That is an orbit type, order type of capital of some point. That's called an orbit type. There are exactly 3 here. But in general, if you take some other contraction map, there can be other types also. Apart from the constant sequence, increased sequence and decreased sequence, there can be other order types also. Other order types are also possible for a general contraction map. For example, if you take the map minus x by 2, again from R to R, this is also a contraction map, and for that we get a flipping. For example, start with 1, next is minus half, third one is 1 by 4, next is minus 1 by 6, and so on. I say that it is flipping, it is crossing sides to 0. From the positive, next term is negative, next term is positive, and so on. Then looked as an order type, it is a different thing. It is a fourth type, let me say, on the type that we have seen. First, this again is not a hard question. You can first ask how many other types are possible for contraction maps in general. There are so many contraction maps. Are there other order types possible? And we observe, again, not with great difficulty, that there are uncountably many other types possible, even for contraction maps. Because for some contraction maps, splitting may not happen. Something in the right side may come nearer to 0, but in the right side itself, the possibility is there. Then, after 2 or 3 instances, it can go to the other side. There, it can remain for certain number of instances of time. Then, such contraction maps can be constructed. I am going to construct more examples also now. I said a little while ago we are interested in the long-term behavior only. Therefore, instead of this order types, I am interested in eventual order types. Eventual orbit types. 2 order types, you can take orbit types. Suppose AN and BN are there, are said to be of same eventual type if some tail of AN, by tail I mean only the first 2 terms and start from, and some tail of BN are of the same order type. If that happens, it may not be the same n naught from where both start. There is an n naught circle, first n naught comes located here. There is another m naught circle, first m naught comes located here. What remains, they are the tails. If they are of the same order type, then we say that they are of eventual orbit type is same. We are asking how many eventual orbit types are possible for a contraction map, and again the answer is there are uncountably many types possible. We have seen some examples of types. I want to give names for them. I will give them a notation C for the constant sequence. That is, if you take the fixed point itself, its orbit type is C. I will use I for increasing sequence. Actually, I will strictly increasing sequence. I will use D for a decreasing sequence. I will use F for a flipping sequence. Particularly, every time it will move from left to right or from right to left. And I just now said that apart from these four which we have explicitly seen, there are many others. I'm going to introduce notations for many others now. I gave one example. This is the real line. Suppose 0 is here. Unique writing fixed point for the transaction map. Can be any other thing also. I'm taking 0. And suppose I start with an element A here and I look at f of A. It's not necessary that f of A should be on this side or that side. Anything can happen depends on the map that is given to me. Suppose f of A is here. And suppose f square of A is here. Suppose f cube of A is f cube of A has to be still nearer to 0. Suppose it is here. Suppose f power 4 of A is here. F power 5 also can be here or there. All these things are possible by constructing more and more examples we are going to say. See, for this particular order type, I'm going to give one such name for that. A is here. It is moving to the left side. Therefore, I will use L for left and R for right. A is moving to the left side. This is also moving to the left side. This is also moving to the left side. But this is moving to the right side. This is moving to the right side and so on. I am writing a sequence like this. I write L. The nth term is L. If f power n minus 1 of A moves to its left side, that is f power n of A is to the left of f power n minus 1 of A, then I put the nth term as here. That is how this LLR sequence is constructed. It is easily seen that if two sequences are of the same order type, then if this construction is taken, this will be the same for both. For contraction maps, it is seen that this alone is enough to see the orbit type itself. In general, for non-contraction maps, that may not be the case. That is, two sequences can have the same LLR sequence, but still they may not be order equivalent. The possibility is in general there. But for contraction maps, this determines the orbit type. And because we can write so many ways in which this happens, and because I can prove that all these are realized, that means there is a contraction map for which any such sequence is coming as an orbit type. Therefore, there are uncountably many of them. I will rather say that contraction map knowing so. There are many, of course. One standard example is this particular map, x by 2 sine 1 by x. And this is an example of a contraction map for which, if you take different points, real numbers, and work out all these orbit types are occurring there. For some point or the other. That part may not be obvious, but that's true.
X, the variable X limits, because you have written sign on our X.
Yes. If X is not equal to 3.
That's right.
Yes, it is finding out, because I have written sign on our X. F of 0 is 0. This is how I would have written. This is an example of a contraction map. It contracts distances by half a meter. This map exhibits all such things as orbitals. Now, for one map, for example, for x by 2, we have easily seen that there are 3 orbit types, C, I, D. These are 3 eventual orbit types. If for a map I am able to describe all possible orbit types, then I say that I have understood the dynamics of this. These are the eventual orbit behaviors. There are three kinds of behavior for this particular map, and therefore the dynamics is completely understood. And this itself is called, I am calling it as, is the package of eventual orbit types. For every element there, if I take the trajectory, either it will be like C, or it will be like I, or it will be like D. That's the meaning. The package is given for this. If some other contraction map is given for that, there will be another package for that contraction map. For every contraction map, there is a package of eventually orbit types. It will be a set. The elements in that set will be orbit types themselves, orbit conform notations. Now I am ready to state my theorem 1. There are exactly 8 packages. Possible for contraction maps on the element. For this map, this package is calculated. For some other map, some other package may come. So for example, for minus x by 2, I said f is flipping package. A flipping type is also included in the package. In this way, contraction maps, there are plenty of them. There are uncountably many of them up to quantity also. And orbit types also, there are uncountably many. But if you look at packages, there are only finitely many. There are exactly 8 only. That is, if you give a contraction map, calculate its package, it will be one of the 8 in my list. Even though in my list of that 8, some lists may be big lists, uncountable. The package itself may be uncountable, or the package itself may be finite, or package is countable. Many things are possible in the package, but the number of packages is only 8. That's what I want to say. Now I am opening my statement here. Theorem 1. For contraction maps, it may be from interval to interval or from real time to real line. The eventual orbit types can come in exactly 8 packages. Example, for the map x by 2, the package is having 3 elements. For the map mod x by 2, the package is having only 2 elements. I'm now noticing the 2 elements may be C and D, may not be C and I. Mod x by 2, there is a decreasing sequence converting to 0, and there is a constant sequence. This requires a correction, not I but D. For the map minus x by 2, it is C and F. F is flipping. These are the only 2. Already I have listed 3 of them. I am saying there are only 5 more possible. I'm going to say this flipping in this kind of notation, that flipping type is written as LR, and so on. Now I am taking another example which I mentioned here. I have written minus x by 2 sine 1 by x. There it is L R whole power n means you can take any sequence of left and L and R symbols together with this constant sequence. That is the package for that, and therefore it is uncountable. Now I am Giving another example, fx is x on -1, 0. If you want to work on the whole real and x on the negative side. But this particular example, x by 2 sine 1 by x on the positive side, then this is another contraction map, and I'm again looking at it. This again may require a correction. Maybe like that. I have calculated the packages. Package is take those elements which are sequences of L's and R's where L is forbidden. That is 2 times you cannot move to the left. Once you have moved to the left, the next you are forced to move to the right in this. That is why L is forbidden. Then include C also. That is the package. In my 8, this is one more kind. Okay, I said I will present 4 or 5 theorems today. In fact, there are 5 in this, but I am saying 4 or 5 because with 4 my time may be over. With 3 my time may be over, but I will roughly present my 4 tasks. For theorem 2, I want to give you a background now. Here I have written one cycle forces only one orbit type. For that I want to give you an explanation. One in general n cycle means some element, say x, fx, f of x and so on. It so happens that n time we come back to x and n is the least circle. N is the least positive integer such that f over nx equal to x. Then I say that there is a cycle there and the length of the cycle is n. Next I want to explain the word forces. First one is not easy thing to explain, therefore I pass on to second one. 2 cycle forces, exactly 3 orbit types. 2 cycle means one element x is going to fx and f of x is back to x. This is a 2 cycle. Then I am writing x less than fx equal to f square x and f2x of course is equal to this and so on. That orbit type is this particular kind of type. This is one. It forces, I'm saying it forces some other orbit types also. This is one orbit type. It forces another orbit type means the following. In every map from R to R, if you find some element of this type, automatically you will find some other element of some other type. If that happens, I say that this type forces that type. For example, this forces a fixed point. Fixed point type we call it as C. Constant sequence will be forced. Why? This is a consequence of intermediate value theorem. If x is less than fx and then F square of x is again you are coming back to x. F square x is less than fx. Something like one element x has moved to its right side, another element namely fx has moved to the left side, then intermediate value theorem says some element between those two should be stable, should be a fixed point. Therefore, this fixes this type. This fixes one more type also, that one more type is start y, bring fy to the other side, x move to the right side, y moves to the left side, and then after that x by y becomes this. This is some kind of a dual of this type, but this will force this. That is, whenever this type is there, you will automatically find this type is also there. You can simply take fx equal to y. You will find that this type is there. Therefore, I am saying this type forces not only itself, it forces this type also, which is a dual of it, and it forces this type also, which is a constant sequence. Therefore, totally 3 are forced. I am writing 2 cycle forces exactly 3 orbit types. Next I am saying, yes, there is one 4 cycle called a simple 4 cycle that forces countably, infinitely many orbit types. I will explain that. Suppose you take an element A, is going to f of A, is going to f square of A, is going to f cube of A, this is going to f power 4 of A. That is some middle part. All the odd terms at odd times is on this side, at even times is on this side. Such a kind of a 4 cycle, not all 4 cycles are of this kind. This will be called a simple 4 cycle. If you take a simple 4 cycle, then we will have calculated what are all the possible types first, forced by that. That is, whenever you find this, what are the other types that have to be presented, and they have even listed all of them. That becomes a countable infinite set of. That's what this next one says. These are already known results. Now I am coming to the new result. Which cycles will force uncountably many orbit types? That's the question I am asking. Not the 2 cycle, not the 1 cycle, not the simple 4 cycle, but some others will force. Which ones? For example, if you take a 3 cycle, it is known that it will force uncountably many orbit types. Long ago, there was a paper in 1965 in American Mathematical Monthly. Period 3 implies chaos, like 2 authors, Lee and K. And I understand that this Yorke is going to deliver a lecture here, right? Okay. Yes. It is one of our speakers. He published a paper with this title, Period 3 implies chaos. What he meant is, if you find a 3 cycle, then you are bound to find in the same function many other types, plenty of them. So I'm not going to explain this word chaos. There will be such a complicated nature there that so many other orbit types are automatically forced by the presence of this 3 cycle. For us, 3 cycle forces uncountably many orbit types. That's enough. Now I'm asking, some partial results are known. 3 cycles like that, 4 cycles, simple 4 cycles not like that, and so on. I'm I want to settle the question completely. Which cycles will force uncountably many? Which cycles will force only countably many? Which cycles will force only finitely many? Now, my theorem 2 is a complete answer to all these, and the answer is stated like this. A cycle forces uncountably many orbit types if and only if it is non-simple. I said that all the odd terms are on one side and all the even terms are on the other side of some material point. In fact, it should be further said that after this, suppose you consider FA, F2 gate, suppose it length is more than 4, suppose it is 8. Suppose F power 5A comes here. Then under F square, if you consider, this is one element Y. F square of Y is this. F square of Y is this. Here, under F square, the even term has gone here, the odd term has come here. I said that the simplicity is violated here. I will try to explain it further. It's not enough if all the even terms are on one side and all the odd terms are on one side. I want more. What I want more is under F square also. This side becomes invariant. There again there could be a middle point and all odd terms to be one side, all the even terms to be one side. Not only that, under F power 4 also same thing should happen. Under F power 4, this part becomes invariant, this part becomes another invariant. There also there could be a middle one, and all the even terms should be on one side and all the other terms should be on one side. If this happens every time, then I say that this cycle is simple. For a given length, there may be many simple cycle patterns, but every simple cycle, it can be proved that it forces only countably many orbit types. Whereas if you take a non-simple cycle, like a 3 cycle or even for a 4 cycle, if the pattern is changed, then there are 4 cycles also which force uncountably many orbit types. I am repeating what is written here. The cycle forces uncountably many orbit types if and only if it is not simple. This
left side, right side business, nothing but only for some modern sets or R, isn't it?
On real line only, please. Real line. And everything is done only on the real line, not for general computing. This has recently appeared, Topology and its applications. In that journal, 2023, just a few months ago, software is a provider. Now I am going to the third. Third one is its main theorem is stated very briefly. It says all jumping times are cycle lengths. I will explain. I will take 5-10 minutes for explaining. Again, I am working in the real line. I take an element A. I ask where f of A is, maybe I get it on the left side or the right side. Suppose it is like this. Then f square of A can be anywhere. All possibilities are there. It can be between these two also, it can be to the right of this also, it can be to the left of this also. Now, if suppose it so happens that for some n, f power n of A is on this side, and n is the least such. By that I mean, if you take a f square of A, f power A up to this, all of them are on that side. That is the first instant when it shifts n is the least such, and rewriting this, n is the least positivity such that f of a and f over n of a are on different sides of it. Could be the other way around. And if n is 10, say, the other elements like x, y of a, x cube of a, all of them are on this side. Maybe below this or maybe between this, many possibilities are there. But n is the first instant when it comes to this side. If that happens for an orbit, then I say that n is jumping back. For a, for the element a with respect to this function here, the time of jumping, a itself is considered as something like a ball, say, that the ball is jumped over. That time is jumping time for every point a is defined like this. For some points, jumping time may not be there. That is, if it started moving on one side, it can every time it can be moving on that side itself. The possibility is that a is never jumped. That is also possible. If for an element jumping time is there, the theorem says that these jumping times are cycle lengths. What it means is then there is another element b such that f power n of b equal to b, and this is an n cycle by the timing n is the least integer such that f power n of b equal to b. If there is one element a for which n is the jumping time, automatically for the same function, you can always find another element b for which the same n is the length of the cycle. That is the meaning of the proposition here. All jumping times are cycle lengths. If you take any function, continuous function, continuity is needed from real line to real line, then all jumping times automatically become cycle lengths. That is, for every element a, look at the orbit. If that orbit jumps at all, not the jumping time, then you will find another element b for which b is a period. That's what this means. For the significance of this theorem, if you know the previous history of the problem, it will be interesting. People have proved many particular cases of it earlier. For example, one of the earlier papers from 20 years ago says that if a is less than fa, less than f square a, but f cube a comes here, then implies there exists b such that b less than fb, less than x square b equal to f cube b. This result is already known. In my terminology, what this means is a particular case of jumping time 3 implies there is a 3 cycle. That's what it means. Now I am saying not in the other cases also. Other case means it may be like this. Then also it will happen. But that alone may not be a significant improvement. I am saying that this 3 is also not important. 3 may be here, 4 may be here. Then I think there will be a 4 cycle. In this way, this theorem is a very satisfactory improvement of many results previously known. For example, this result. There are some other similar results which are also known and come in textbooks also. But all of them become particular cases of this. Every passing on to the third theorem, passing on to the fourth now. I will spend more than 5 minutes for that. Maybe this is the last I'm going to say today. I have used one new word there, T-simple, for a map. T-simple map is my own word, coined by me, to say that there are only finitely many orbit types for this F. F is a continuous function from R to R. If you take any point, there will be an orbit type given by that point. Points are of course uncountable, but if the orbit types gathered through that, what I call as a package of orbit types, if there becomes a finite set, then I say that this map is a T-simple map. For example, if you take X square, I am no longer doing the transactions as any continuous map. X square is a map from R to R, and it can be easily done, have been done as exercises and textbooks, etc. And there are only 5 types. For this map, under this map, whatever point you take, its orbit type will fall within one of the 5 listed there. Then I said, okay, then this map is T-simple because it is admitting only finite many orbitals. Now I am asking the question, what are all the orbit types available for such maps? For maps which admit only finite many orbit types, those orbit types I want to characterize. What are they? It can be put in another way also, using the word forcing. This word forcing itself was in the 1960s introduced by A.N. Sarkowski. He used it in this sense. N cycle forces N cycle means M and N are 2 integers, positive integers. M cycle forces N cycle means for every continuous F from R to R, if F admits an N cycle, then same F has to admit an N cycle. If there is a point of period M, there will be another point of period M for the same function, and this should happen for all continuous maps. M and N are fixed, F is varying now. Whatever continuous map you take, if you find an N cycle, you will automatically find an N cycle. Then it is said that M is forcing that M cycle is M cycle forces N cycle, and he proved some remarkable theorem which people would not have guessed at all. He said that 3 always forces 5 in the sense that whenever a real continuous map admits a 3 cycle, the same map will have to admit a 5 cycle. He used this kind of notation, and then he proved in 5 it admits 7, forces 9 and so on, and after that, all these things, force 6, then 10, then 14 and so on, I multiply them by 2, then comes 12, 20 and so on, 28, and so on. I have multiplied these by 2. In this way, all numbers are coming in one row of the other row one, except the powers of 2, those he wrote in the last line, some 2 power and 4, also 2 power 2 power 1, and lastly 2 power 1. Now all natural numbers are being arranged in some other total order nowadays known as Sarkowski's order. And in this order, the forcing relation is happening on the real line. That means, suppose you take this 5 and 14, 5 is coming before 14, it means that 5 forces 14. That means that for a continuous self map of the real line, if you find a 5 sided, you will automatically find a 14 sided. Now, this started in 1960s, and extending it. Saying I am extending it people earlier and extended it not only for the cycle length but for orbit types also. One orbit type forces another orbit type, same kind of problem. Orbit type and orbit type forces another orbit type. Suppose this type is, I am calling it as S, this I am calling it as T, means same thing I am not repeating. If you take any continuous function f from real line, in that if you find this orbit type present somewhere, then it is necessary that this orbit type is also present for some other point. Instead of cyclic, I am generalizing it. Okay. Now I am asking and completely solving this question: which orbit types force only finitely many orbit types? For example, this 3 cycle is not so, because 3 is forcing so many things. Whereas if you take this 2 power 4, it is so, because after that I am finding only finitely many. This is among cycles. But the same 2 power 4, I do not know whether it is forcing only finitely many other orbit types, because among the cyclic ones there are only finitely many. There are non-cyclic orbit types also. I am saying that 2 power 4 is also not there. Which things will be there? That question is a reformulation of the previous question for 3 simple maps. Which orbits will be available there? The 2 questions are really equivalent questions. If you find a D simple map, what orbit types are present there? That question and this question which is written here, both have the same answer. That they have the same answer is easy to see, and that is fully answered here. The complete answer is there are exactly 10 eventual types there. So there are infinitely many types on the whole. This paper has already appeared. Journal of difference equations and applications from 3 years ago. That's already. Now I am going to stop because I am finding that my time is up. Universal property I am saying. This I am not presenting now. And I am leaving it. I am welcoming questions from you.
Any questions?
Excuse me. You started with
Contraction maps.
contraction mapping.
Yes.
And then you proceeded with the type, order type and
Yes.
so what exactly is the conclusion that I get?
Yes. I will say. I presented 4 or 5 theorems. First theorem alone is on contraction maps.
Yes.
Second theorem onwards, it is for all continuous maps from real line theory.
Oh, right.
for the first theorem, it says that if you take the package of orbits, for contraction maps, only 8 packages are possible. That's the theorem.
There is sanctity for X by 2 and 7.
I want infinitely many oscillations, therefore I go to X sin 1 by X. But I divide by 2 because I want to make it a contraction map.
He was not work. He was cosine will not.
Cosine will. Cosine. Cos also. What properties are required? It should become a contraction map and it should have infinitely many turnings in its graph.
The book for reference is it topology only or?
Sir, but these theorems themselves are new, if you can't find it. But book for reference, there are books, elementary books on dynamical systems or topological dynamics. There is one by R. Home. Introduction to Dynamical Systems. Oh, I am giving that book because it is written for BSc students, undergraduate students. It is an undergraduate text in math. There are many other books which are written in still higher levels.
Can you extend this theory to complex plane?
Yes, there is a big branch called complex dynamics is a special branch of dynamics. But many things are special for complex dynamics. We cannot think of such theorems that there. You may have heard of something called Julia sets. In complex dynamics, we discussed this complicated behavior of dynamics through Julia sets.
Julia
Julia.
Because the left and right distance we can talk in terms of.
Right. This doesn't happen.
Circle, because circle you can say left side and right.
Even in circle, many of these theorems fail. For example, if you take the plane is also a complete metric space, there are contraction maps on it. If you ask how many packages types are there, then because this order is not there, we can prove that there is only one type. Okay. Any two contraction maps are the same pattern.
So, given that, can you fix up which are the finitely many things?
Yes. Just by looking at the graph up here, we can say among these 8, which one? In fact, that is how the proof goes.
If the orbit is dense, then things are bad.
True. Only thing is for contraction maps it cannot become dense. For other maps, orbit can become dense. Then we say that chaos is entering. Yes, you are.
There are any more questions? There are any more questions?
Any more questions?
If there are any more questions, please do ask. If there are no questions, I wish to thank Professor Khanna on the topic that you mentioned about what is dynamic. And it's real dynamics. Okay. Thank you.
Thank you.
Thank you for the enlightening talk, sir. Now I request Dr. Shivaram sir to hand over the mantle to Dr. Lee. Thank you all. Now we have a panel session. Invited talk one by Dr. Narayan C.K. The venue is the current venue, that is the seminar hall 1. And next, the invited talk 2 by Dr. Kiran B.P. It will be, the venue is seminar hall 2, that is the multimedia hall. The volunteers are there outside to guide this.
Talk by Dr. C.K. Narayanan, entitled as Analyzing and Improvising the General Availability of Meta-Learning Approaches for Fuel Cloud Learning will be held here, and talk by Dr. D.B. Kiran Kumar on Synthetic Spectral Theory will be held at the other seminar hall.
Those who are sitting in the back, if you like to come forward, it will be visible for you.
Beginning the first lecture hall, I request Dr. Manilan. I request Dr. Manilan and Swami from the University of Kerala to chair the session.
So let me invite the speaker. The speaker, Professor Narayanan is mainly focusing the questions that arise from having to learn with a minimal supervision and the driving force behind his main research. And his current areas of interest are in the development of generative, generalizable, and explainable models. And his research has been published in publications like AICMDD, as well as the conferences like ICML, ICCAI, etc. And he has been recognized with the exceptional reviewer honors at Neural Ideas and participates in program committees for other conferences. Additionally, he recently co-chaired the DST and Humboldt Foundation organized Indo-German Founders of Engineering meeting in the ICMDD meeting in 2021. Funding for his research comes from both the business and the DST. In addition to working as a research faculty member at Washington State University, he received his PhD in computer science and engineering from Arizona State University in 2010. He worked as a faculty member in the computer science and engineering department at IIT Roba before moving to IIT Palakkad. Currently employed at IIT Palakkad and head of the Department of Data Science and SMS. So I invite Narayan, please go ahead.
Thank you. Thank you for the introduction. I find myself perhaps at a very difficult situation, right? We had such an erudite lecture preceding my talk, and I hope that I can at least do 1/10 of what Professor Kannan did during his lecture. I am also a little out of place because the meeting here is, the gathering here is of all mathematicians. Though I have a mathematical background, I'm more into machine learning and the computer science aspects of it. So you may not find a lot of theorems, a lot of equations in my talk, but I hope I will be able to convey to you some of the recent developments in the learning community. That will be my objective of the talk. So I will have to skip some slides and probably discuss a little more detail the applications and the intuitions behind some of these approaches. So let me begin with what is meta learning. And in this talk, I will talk about two specific aspects. One is the impact of task distribution, the other is of task complexity experience. But in order to understand all of this, first we have to know what is meta learning. And the origins and the inspirations of meta learning comes from human learning. So humans acquire new concepts and skills with minimal exposure, and that is because we leverage our past experience. To give a very simple example, if one knows how to ride a bicycle, he or she may be able to quickly learn how to ride a motorbike compared to a person who doesn't know how to ride a bicycle. Right? And if some of you are familiar with programming, then you may know that if you know C++, it is easy to learn Java than if you have known C. And that is because there are certain tasks, there are certain commonalities across these different tasks, right? So if you know how American football is, and you look at and rugby, there are some commonalities, right? Or another example is if I look at a child, and if a child is presented with comics which contain cartoon figures of horses, and you take the child to the zoo and you spot that object there, which is a horse, the child may be able to say that it is a horse, though it has never seen a horse, a real life horse, right? And that is because the child is also able to leverage its past experience of what is this concept of a horse. So this is how human learning works. And what we are trying to do in machine learning is, can we use this paradigm of learning from past experience to do new tasks more efficiently and quickly? And that entire branch is what is referred to as meta learning. So we would like machine learning models to leverage experience from past tasks or training for learning on new tasks. And this entire paradigm is primarily focused towards some of the state-of-the-art machine learning models. So just by a quick show of hands, how many of you are familiar with machine learning? Okay, all right. So I'll try to simplify that further. Basically, what we're trying to learn is a function from one domain to another domain. So just a function f from r power n or r power d to, it can be a finite discrete set, it can be a continuous number. Right? That's all from a mathematical perspective, that's what we're trying to learn. What you all might be familiar with is a specific form for this function. This function f of x might be sin x, this function f of x might be x to the power 4 into sine 1 by x plus cos of, x to the power 3 or whatever. You have a very, very complex form that you explicitly state for this function, right? That's what all of you are familiar with. In machine learning, we have a set of, a model called neural network models, where you give the input whatever x is, and you will get whatever the output you want. But you don't have an explicit form for that function. Do you get what I'm saying? Just like how to wrote the equation for that function, we may not have exactly that equation, right? But the function is implicit there in some particular way. And neural networks are referred to as universal function approximators. That is, you take any function, right? You can create a neural network which will approximate that particular function. Is that clear? Yes? I hope I'm making sense to you.
Neural network meaning?
Yes, so neural network means not a real human neural network, an artificial neural network. So in order to, now I think I would need the board. I think now I understand my audience better, I will be able to convey even a simple concept, right? So when I meant neural network, I meant artificial neural network. And artificial neural network is basically using basic principles of how a real neural network works, right? Right, so why is there setting it up? So modern day, you see, I mean, you might have seen lots of news articles which talk about how AI is revolutionizing our way of life, right? And the fundamental technology or fundamental models which is driving these advancements are basically artificial neural network models, or they are also synonymous with deep neural network models. The term deep essentially means you have multiple layers. So I'll just quickly explain what I mean by multiple layers. So you have at the first layer of input. So let me take a very simple example to explain this to you. Let's say we have an image classification task. What does that mean? I present an image to you and ask, what is the object which is present in the image? So if I show an image of a cow, you will say it's a cow. If I show an image of a horse, you will say it's a horse, right? So the input to your model, what your function is, so in the mathematical sense, you want to learn a function f. What is the domain of this function? It is the image, right? What is an image mathematically? It is basically, let's consider a simple grayscale image. What will it be? It is a matrix, right? So you'll have, say, n rows and n columns. Each element in that matrix corresponds to the pixel intensity at that particular location. You can kind of roll it out and say it is in some R power d space. Right? D will be m into n. Right? So one large vector you have. This is vector. Good. This is the domain. And what are we mapping it to? In this case, a set of classes, right? Cow, horse, donkey, lion, and so on and so on. So this is the function that we are trying to learn. But you may ask, well, these are symbols. What do you mean by, this is your output range? Well, these are symbols. I map these symbols to. So what I mean by this is I can represent my cow as 1, 0, 0, 0, horse as 0, 1, 0, 0, this as 0, 0, 1, 0, and finally this as 0, 0, 0. There is no specific order between them. They are just different elements of that set. And this is a specific representation of the set, and that is referred to as a one-hot encoding. Right? And my goal is to learn this function f from this R power d space to essentially this particular space. Okay? So that is what is a simple image classification task. Now, how is this performed in neural networks? Well, you are passing the input X, and this input X is connected to a whole bunch of nodes which act as your neurons, right? So your every input is connected to every other output, say, of this particular thing. So there is some processing that happens there, and the processing is very simple. It consists of an addition operation. It is not just simple addition, it is weighted addition. So you do Wi Xi. So you weight the inputs and add them up. So it's just a weighted addition. Say I is equal to 1 till B. And if I just do this is a linear operation, right? So what I do is, on top of this, I apply an activation function, and this activation function is typically normal. And the activation functions which are typically used in neural networks are sigmoids. Sigma of x is 1 by 1 plus e power minus x. You have damage activations, you have rectified linear unit activations, and so on. So you have a variety of nonlinear activation functions. So now this is one layer. So let's call it as layer 1. Okay? I can take the outputs of this layer, which is coming out of this particular function, and pass it as input to another bunch of neurons, another layer of such neurons. I can go on doing this, and finally I have my output data where I have the output 1 0 0 0 0 1 0 0 and so on. So those 4 outputs which I described before. Depending upon which one of these has value closer to 1, I can say that that is the corresponding class value of the symbol to be written. Did you get a sense of how a neural network works? Yes? Yes? Great. So the more layers we add, this becomes a deep neural network. It's very deep. And the way we train such a neural network is through the fundamental algorithm is gradient descent. We have studied in calculus, right? So we have a function f and we want to minimize the function. We find the gradient and go in the opposite direction, take some small step and keep on doing it, and eventually we reach to the optimum. That's the same principle which is also applied here. And this is not something new. The idea of this neural network, artificial neural network, and the gradient descent algorithm which it uses called the backpropagation algorithm was proposed way back in the 70s or 80s. It's still the same algorithm. But why it has been so successful? Well, 2-3 factors. One, now you have access to large amounts of data. Second, you have access to systems which can do parallel processing in an unbelievable or unprecedented manner. That is what we call the graphical processing units, GPUs. And these two are the main factors which has caused this explosion of models which use AI. Right? So, where I go back is, so you have this deep neural network model, right? So, can you tell me, what is it that I want to learn in this neural network? So that I get a good output for a corresponding input. What should I learn? X is fixed, output is fixed, the activation functions are fixed. What then can I change in order to get a good output? The weights, right? So we want to learn these weights. That's the goal of the learning process of a neural network. And the way to learn the weights is through gradient descent algorithm. So one way you can look at, right? So now learning these weights is your machine learning algorithm, right? But when I'm starting, right, I initialize these weights randomly. I don't know what weights to select. I initialize them randomly, and I hope that the training process, which is basically trying to minimize the loss through gradient descent, will learn automatically what are these weights. By the way, the loss function of typical neural network models are extremely nonlinear and they are not convex losses, convex functions. So you cannot expect to reach a global optimum. You may get stuck at a local optimum. So that's the fact of training deep neural network models. So I take this weight and I say, let me initialize randomly, and through this gradient descent process, I can converge to a good set of weights. When I say good set of weights, the neural network which I have learned will be a good functional approximation from this particular space to the output space. So that is what is the goal. Now the question comes, suppose I have already trained a network which is, say, good at learning or predicting Malayalam script. Okay? Malayalam language. So the input to the model is Akshara written in Malayalam script. Output is what Akshara is written. Okay? And now suppose I want to learn a new model for Tamil script. Right? It makes sense that I can start using the weights of the Malayalam script as a starting point and then train the model. Yes, instead of starting it at random. Why is that so? Why is that so? There are certain properties, the way we write the cursive style in Malayalam and Tamil scripts, which overlap. And since my network there is essentially looking at visual characteristics of the letters, the characteristics which has learned for one language may be applicable to another language. Yes? And therefore, a good solution would be to initialize these weights using the model which has been learned for Malayalam script and then do the training process for Tamil script. Obviously, if you just use Malayalam script, it's not necessary that you will get a very good output. There may be a lot of errors, and those errors can be minimized if you try to apply training process to gradient. And that means you need a lot of examples for Tamil script to do the training process. So from the machine learning model's perspective, one experience or one type of experience it can leverage from the past tasks is this set of weights. These weights here encode its understanding of how to do a particular task. Is that clear? Yes? Right. The other experience, right, is so initialization is one such experience. The next experience I will say is, so if you are familiar with, are all of you familiar with gradient descent algorithm? Optimization, gradient descent? Yes? So the basic step is the following, right? W new is assigned as whatever was the old weight minus, you have some factor eta times the gradient of the loss function with respect to the weight, right? And this is actually evaluated at W. This is your simple gradient descent equation, right? So this is the direction of the gradient. We want to traverse in the opposite direction. Eta tells you what is the step size, how much you should go, right? Another experience that you can gain is what is eta? By how much should you go? So step size, right? So by the learning rate, the step size eta is also called as the learning rate, right? So you can learn what is that optimal value from your past experience. So in this example, I said this is the equation, the training update that we are sticking into, right? But a more revolutionary idea would be, I am not going to stick to this. This means what? It has this nice property that we are depending on the gradient multiplied by some factor to tell me what should be the outcome. Right? So I can rewrite this entire thing as W mu is some function g. The argument of this function is whatever was the old weight, or perhaps the history of how those weights, the trajectory of how the weights have changed, and whatever is the current weight. Here we have an explicit form for the function. Now I am saying I have another function g which tells me what should be the result. Now this function g is another artificial neural. So you have a neural network itself which is guiding the optimization process. So when I say you can have an optimizer, I am learning an optimizer. That's a very interesting and very novel revolutionary idea, rather than just sticking to one specific equation which has a specific form. It can be in terms of decay coefficients which are used in the optimization or momentum curve and so on, or it could be even in terms of distance metrics. So you want to talk about metric spaces, right? So you have well-defined notion of what is a metric. It has to satisfy certain properties and so on and so forth, right? So these days we also talk about learned distance metric. That means you have a neural network which tells you what is the distance between two objects. It need not necessarily satisfy all the properties of distance metric as it is known, but it serves the purpose of distinguishing different elements. So you have a neural network again which is trying to measure what is the distance between or how different are two data points. All these are experiences which a model can leverage from its past tasks or past learning to apply to a new learning. And that is what is a learning experience for machine learning models, which is referred to as meta-learning. So far, are you with me? At least to some extent? Yes? So the question is how to learn an experience. And fundamental to meta-learning is this idea of a task. And we want to create these tasks in a way we expect the model to face when it is actually being, doing a particular task, right? So, for example, if the task was to learn, say, a new disease pattern from chest X-ray images, right? So you think about the initial days of COVID. You didn't have too many chest X-rays where you had the mappings of this corresponds to COVID pattern, right? We didn't have that luxury. But what did we have? We had large amount of chest X-rays already available, say for TB, for pneumonia, or for many other such diseases, right? And the challenge was, can we build a function F which takes a chest X-ray and tries to predict, instead of these four classes, whether this chest X-ray has symptoms of COVID or not. It is just 0 or 1 function, right? But we didn't have large amounts of samples available for it, right? So you can think again of the same property, right? Whatever has been learned for, say, detecting TB or pneumonia or some other disease, right, may be applicable even in the context of COVID. But there is additional thing that you only have to work with small number of samples or examples. And that is what is referred to as supervised learning. In supervised learning, that is, as a domain expert or an external entity, we are giving to this machine learning model some supervisory information to learn this function F. And what is the supervisory information? Whatever is the class label that is associated with the data points, right? So the task was to learn COVID, say from 10 examples, right? So what meta-learning does is, it tries to create similar tasks using your existing data sets. So the problem of trying to learn a model using very few examples is referred to as few shot learning. You have n classes, these are your classes, but the number of examples you have per class, which is what is a shot or k example, k is very small. It may be one example, it may be 5 examples, it may be 10 examples, right? So that is what is referred to as few shot learning. And the goal is to learn a few shot learning tasks, to do it very well based on past experience. And what meta-learning tries to do is to simulate such tasks using the data set for which we have abundance of samples which are labeled and so on, and try to apply it to the new task that we want to learn. So I won't go into the details of it because it really doesn't matter to explain the rest of the things, but the idea is, by simulating such training settings, the model has the ability to learn experience which is agnostic to the task. That is, experience which is common across the tasks, right? So if it were to learn these weights, a good set of weights, that would be trying to extract some characteristics, visual characteristics of the input images. Suppose these tasks were trained or were designed to learn this optimizer. What would you think will be the experience part of it? What is it trying to learn? You have a loss surface, there is some geometry to that loss surface. An optimizer is learned to traverse that loss surface. The geometrical patterns which exist across different loss surfaces, and these different loss surfaces are coming from different tasks. Maybe one for Malayalam script, one for Telugu script, one for Tamil script, and so on. But the geometrical patterns might be common. So if this function g has learned how to traverse a particular pattern in one loss surface, it may be able to apply that knowledge to traverse another loss surface for a different task. Right? So that is this function g that you can learn. So task agnostic experience could be in terms of the features, right, characteristics from the input images, or it could be how to traverse the loss surface, or it could be what will be a good step size on the learning. So the assumptions that they make during this training process is that all the tasks, so you have a bunch of tasks from where this information is gained, the assumption that is made is all the tasks contribute equally to that experience, which may not be true. And the next is the task distribution and the label space are also common. They are the same, right? So the last is the task complexity. We assume that the difficulty of the task remains the same across your training sets and your test sets. Right? So I'll quickly go over the first part, which is the impact of task distribution on experience, and summarize my task complexity part of it. So the idea here is that meta training and meta test class are drawn from the same distribution. So we have the support set and query set. Support set is used to train the model, query set is used to evaluate how the model performs. And if you assume that there is no violation in the distribution of your support and query examples, right, this is the performance that you get, around say 64% accuracy for a widely known benchmark data set. Now, suppose you have some kind of a shift between the images. For example, the training images are very clean images. You took those images in a laboratory setting that control over the lighting, everything, so the images is very good. But the query images that you have are very pixelated images, right? There is a lot of noise which is present in those images. So the model that has been trained using real images, which are very clean, may not be that accurate when you have noisy images, and that is reflected in a drop in the performance when the model is presented with such pixelated images or noisy images. Right? So when the distribution assumptions are violated, model performance drops. So the goal that we had was, can we make these meta-learning approaches resilient to such distribution shifts? And if so, how do we go about doing it? And in one particular distribution shift, which is even more harder to tackle, is when you don't have access to the new samples, that is noisy samples. You don't know what kind of noise is present in the data. Right? Even under such situation, can we address the distributional shift which occurs in the data? So the current approach is basically uses optimal transport. The idea is you have this is your support set, this is your query set. You expect them to be coming from different distributions, but they are all having common labels. So you try to transform them in using some neural networks, using some functions, which kind of overlaps them, right? So which brings out the commonalities between the two data sets. So that's basically what they do, which uses the optimal transport. But the question, the point is, this optimal transport approach requires the examples from the query set. That means it's a transductive approach. It needs to have access to these examples, even those labels are not available, in order to design how to transform the data points. So our challenge was, you don't have access to this, but from here itself, can you build a model which is resilient if these kind of changes occur in the query? Right? So for that, we do a constraint augmentation. So basically what we try to do, if I were to explain it in a very simple way, is just so what we try to do is, we have a task and we expect the task is coming from a particular distribution. So within the vicinity of the task, we try to find out which are the tasks on which the model that is learned will fail miserably. Right? So those are the tasks which have slightly different distributions on which the current model is failing. So I design my loss such that I want to find the parameters, that is W here, which is represented as theta here, such that the loss over the tasks which are at a row distance from my existing task, the maximum loss on that is minimized. Did I make myself clear? Right? So you look at the task within a specific distance, which is rho here, and among those tasks, you are trying to find out which of the tasks has maximum loss, and we are trying to minimize that. So that's the goal of this adversarial query projection. And since please. Thank you very much. And the goal is to find theta which gives you the best result there. And here we're talking about distributions, right? So tau q is a distribution, tau q naught is another distribution. So you have a distribution of tasks, and you're trying to find out a new distribution tau q, which is at a distance rho from my original distribution. And typically here we use a Wasserstein distance to measure the divergence between the distributions. So in this result we have a lot of other results which say that is there a guarantee that such a distribution exists? Right? What is the guarantee that you will find such a distribution, and you will also find a task which can be sampled from such a distribution? So we justify that theoretically in this work. And the idea is very simple, that you take a current task, you do a gradient ascent, which is adversarial projection.
What the optimal transport gives us? Optimal transport.
Right.
Whether what this gives us?
This will give you a representation for these two sets, which have commonalities between them. It just gives you the representations. Right? Right. So we do an adversarial perturbations, which is, if you have to find out the data point on which the model performs really bad, I start from the data point and do a gradient ascent. So I know in which direction my loss is increasing. And if I traverse in that direction, I can find a data point where my loss is maximum. So that is the basic idea of this approach. And we show it on a bunch of well-known, baseline meta-learning techniques. And so my work is all experimental. That's why we have these kinds of numbers to show that the model that we present is actually performing better than some of the existing models. So this is fine, and this just shows a visual analysis of how these tasks are created. And as the iterations progress, you can see that the tasks are getting harder and harder. So the model is trying to look at more difficult tasks as the training process continues. So let's get this, and I'll talk about quickly, 2 minutes, and talk about the impact of task complexity.
You have 4 days.
Yeah, I'll complete this in 2 minutes or so. So we said we are looking at a few short learning settings. So that means you have, say, 1 example or 5 examples per class, and we're looking at a 5-class classification. So on 4, in this case, it was 4 class, I can have 1 more class. I can extend it to say I have 200 classes, but I have only 5 examples per class, and I want to learn. It's a very, very challenging task, right? So in this work, what we did is, we were investigating the quality of the experience that is learned as a function of increasing task complexity. Whether a good initialization captures the experience part, or a good optimizer captures the experience part, or a good learning rate captures the experience part. So which was the basic idea here. And what we show in this paper is, it's all empirical paper because we did a lot of experiments with large data sets, is that amongst all these different approaches, we have Protonet, which doesn't perform this fine tuning. Note that for Meta-LSTM++ is an approach which learns this function G. Meta-SGD is an approach which learns eta. And NAML is the approach which learns the weights. Amongst all these approaches, if you learn an optimizer, which is the function G, it actually represents an experience much better than any of the other experiences which is learned. And which is what is a very surprising result for us, because you are saying, or rather we are saying that if a function is learned, how to traverse the loss surface, that is very important when you have to do a similar thing on a new task, rather than trying to learn an optimal set, an optimal initialization or an optimal learning. And that's what we show here, that as the complexity of the task increases, a learn optimizer, this function G, performs much better in transferring that experience to do a new task than either the learning rate or the initialization. So that is what is the primary result of this particular paper. And we do various experiments in trying to understand where is this difference occurring. Is it occurring in the logic space that is just before the output, or is it the entire feature space which gets transformed, and so on? We do a lot of those experiments, and we show that if we were to just keep two slides and go there, we say that adaptation to meta-tests. If you're doing this fine tuning, then using a learn optimizer is the best way to do it. And if there is no adaptation happening, like what Protonet does, they use examples to predict what is in the class, then Protonet gives you the best feature extraction, that is the best set of weights. But if you are trying to do adaptation, then using a learned optimizer will be the best solution, right? So with that, I will stop my talk. I hope at least you got some idea about what is meta learning. If there are any questions, I'll be happy to answer.
So this is from the So this is from the one of the points that was raised earlier today from the point of ethics. So having a learned optimizer means that you are depending more on whatever the data we have already, right? Which if we know if it is biased data, then isn't having a learned optimizer going to blow up that problem?
Right. So I agree with you on that, right? So at the end of the day, all these neural network models are rather all data-driven models encode whatever is present in the data. If there is bias in this present in the data, it will of course it will encode that bias unless and until explicit mechanisms are taken into account to prevent it from encoding such biases. I agree with you on that. But when we look at these learned optimizers, they are not looking at the data directly. They're actually looking at the loss surface. Right? They're looking at the loss surface. In particular, they're looking at the geometry of the loss surface. It doesn't matter what data you're working with. If there are similar patterns, what I mean by that is, if say this is one loss surface and this is another loss surface, there are some common properties of the geometrical surface, right? And these optimizers are essentially learning how to navigate these loss surfaces. So data bias really doesn't impact them. What impacts data bias is the set of weights, because that is directly working with the data. I hope that answers it.
Any other questions? So if there is no questions, then I have one more question. Actually, so as I have the continuation of your question, I'm getting some problem. Like suppose like in the application, like you are having the data of your eye scanner. Sometimes they are arriving in the hospital. They are having a lot of data, and based on the data, they are going to predict something that what is really the patient is having the disease. So suppose if the one patient is having the rarest disease, how the existing data will gives you the predict that.
Right. So that's a very good question, right? So in typical supervised learning, we assume that this set or this space is a closed space, right? That is, this function f that is being learned can only do the task of predicting these four variables. Now, when you are saying that in addition to these four, I have a new label now, this function f is incapable of predicting that. That's what I mean by the closed space assumption, right? But there are new approaches which say the function can say it is actually none of these, but I don't know what it is, but it is none of these. That is possible. That is what is called as out of vocabulary learning. This is your existing vocabulary. You want to learn something which is out of your vocabulary. So that is also possible, right? But the challenge is also the fact that you're saying you have very few samples available for this rarest case, right? Even if you take a simple X-ray example or retinal scan, right? If you take all the population, say of Cochin, probably 80% of the scans will be normal. 20% scans may have some abnormality. Within the 20%, perhaps 1% has an extremely rare abnormality. So if you look at that 1% of the 20%, right? And if you look at the overall picture, you have an extreme case of imbalance. Majority of the samples don't fall under that particular category. So there is an entire body of literature which talks about how you learn under imbalanced classes, imbalanced setting. So that means any other questions? Thank you.
Okay, so let's thank the speaker for the wonderful talk, and he explained all the neural networks and what mathematics behind it. And I thank once again the speaker for his wonderful talk.
Thank you, sir. I invite Manivan sir to present the memento to Narayan sir. Thank you, sir. Now we move on for lunch break. We have 1 hour lunch break and we will resume the session next session at 2:30 p.m. We will start the next session by 2:30 p.m. The lunch is in the Chavra Hall. It is behind the canteen. Chavra Hall. Thank you.